another um, three module. This will be the last class for the uh, module 5. So can assume that this CAT 2 or CAT 2 we will be having module 3, module 5. All of them are time dependent fields will be there. So I think we have about one week time study. Start to study, and if whatever the questions you have, we can start to ask about that. So the last class we discussed about the plane wave, how they travel, how they propagate in a given medium. Even without medium, also they can travel. And for instance, in free space, also they can travel. That is what we have seen already. And we also studied the boundary conditions for a normal incident. So if field is, if there are two medium with impedance eta 1 and eta 2, and if a wave incident in a particular in a at a normal angle, then how this reflection will take place and how the transmission will happen. All these things we already discussed about that. So today we are going to see the next possible one, that is the oblique incidence. And of course, we already studied about this pointing vector and pointing theorem and the applications to study the loss, the how the power loss happens in a given medium and what are the possibilities. So now we will study upon the reflection and refraction happens in a boundary of two different materials because of the electromagnetic wave. So we already studied a lot about this wave and how this wave exists in a given medium for a given condition. The conditions are nothing but Maxwell's equations. So from that, how to derive the expression for the field components which are existing. And in that, we have seen that there are two possible wave can exist. One is the forward traveling wave and the backward traveling wave. And both can coexist, or it can exist in a single wave. Means either a forward or reverse wave can be possible. And we have studied the nature of the traveling wave, particularly the plane wave we have seen. So in case of plane wave, you're supposed to assume that the wave front will be having a common phase, which is defined by omega. And where the another phase term which is cover up the the space, so which is defined by beta, and this beta defines the phase velocity. And in case of this defines the frequency. So you could see the relationship between them. And in this case, the wave is actually traveling in a particular axis. So let's say if it is in the x-axis, then just perpendicular to that, we will be having the magnetic field, and the wave is actually traveling in the z direction. So I think you are familiar with this by now. And we have seen how this wave will exist in different media. When a lossy medium is coming into the picture, this conductivity will not become zero. If the conductivity is not equal to zero, then you will get a new term called attenuation constant. And this attenuation constant defines how fast the wave will decay over a space. And this naturally give the rise to the definition of the impedance, how this, when a medium is available and the wave is traveling in that, and how this medium is trying to stop this the wave, because this is carrying energy, and this energy may disturb the equilibrium of the material. And ultimately, the entire or the whole theory of the physics is lying on how to make the energy level equal to zero. So obviously, all the material tend to do that. And this is so therefore there are two mechanisms could exist. One is either the energy supposed to be zero at any particular space or time, or at any particular space the incoming energy will be equal to the outgoing energy. Therefore the law of the conservation is preserved. So in that regard, there will be a coexistence of the resistivity or the impedance for a given medium, and that defines the ratio of the electric and magnetic field. Therefore, impedance is the uh, the property which is actually enabled by the electric and magnetic field, and it is a variable one with respect to the behavior of the electric and magnetic field. So whenever there is a phase difference, obviously the impedance also will come up with some phase coefficients. And this eta, you can see that it is largely depends on the three important properties, and the fourth one is the angular frequency. So which is one of the another property which we can say that of the wave. So therefore, whenever there is a change in frequency, the impedance will go increase and decrease. So this is very important one for the consideration of the uh, development of communication system and many other aspects. Okay. So we will see this same impedance equation in different behavior for different structures. For example, whenever you have parallel plates, obviously you will be seeing the capacitance. And when you see the impedance of this particular media, then you will see that either electric or magnetic field will be dominant. In the capacitor case, electric field will be dominant. And that is going to define this overall behavior. And similarly, it is the same case for magnetic fields, which are addressed by inductance. So we will see that how the same behavior in a medium can be artificially created by yeah, RLC equivalence in the very near future. In the next module itself, we are going to discuss through transmission line theory. So we have discussed a lot, and then we move to lossless dielectric media, and then in a good conductor, uh, how this good conductor defines uh, the propagation. And we can clearly see that since the conductivity is very large for the metal or conductors, then the decaying fast will be very high. So which is defined by the skin depth. The skin depth is the penetration depth from the surface of the incident towards the medium good conductor itself. So for as frequency increases, you could see that there will be a fast reduction of the amplitude. And then we studied about the Poynting theorem. The Poynting theorem at the end, it describes that the power which is defined by the cross product of electric and magnetic field over a given value. Let's say there is a volume is available and it is covered by the maximum surface ds, and the electric and magnetic field which is actually traveling, let's say electric field and magnetic field are available, and the cross product obviously will be available in this direction, which we call Poynting vector. This Poynting vector can be calculated over a surface. So this will be equal to two things. One is the rate of change of magnetic field with respect to time, and then the rate of reduction of the electric field square. This can be also calculated with magnetic field. And since the conductivity is zero or not, that defines the loss. So the overall loss of the given electronic system or microwave system or the wave propagation largely defined by this uh, conductivity, which is actually characterized as a ohmic loss. And similarly, this same square of the electric field, which defines the uh, and with respect to rate, obviously we will get the power. So this power, which is nothing but the rate of change of energy. So this is the energy term. There are two possible energy: one energy with magnetic field, energy with electric field. So if a structure can store the electric field or magnetic field, so that defines the overall behavior, and that is going to greatly affect the overall power, which is constituted by this electric and magnetic field. So if we assume the material is lossless material, then conductivity will become zero. There is no ohmic contact. Therefore, the medium is going to store all the energy by the electric and magnetic field. And if the medium is completely closed, let's say you have a metallic structure and you are closing, and through your opening, you are sending the microwave, then it is going to store the energy in terms of electric and magnetic field. We can even calculate the value. So this immediately give the rise to the impedance, and that you can clearly see with respect to this, the port where the wave is actually coming. And this will immediately give the rise to the port impedances. In the future, we will see port impedance and the load impedance, all the cases. And that is where the pointing theorem will be more helpful. And we have seen how to calculate the average power density for a given wave. Then we move to boundary conditions. Okay, so far now we have discussed about the wave in a single medium or in a homogeneous medium, but in a heterogeneous medium, particularly wherever the material is clearly defined with the boundary, we can find how the wave travels from one medium to another medium. And since the wave is traveling in a particular direction, and there will be two wave can exist. One is with respect to the incident wave, there is amount of energy can be transmitted into the second medium, which is called transmitted wave, and there is a wave can reflect back, and that is reflected wave. So according to uh, the the solutions what we have seen in the Maxwell's equations for a given medium, the medium which has a particular property. There will be two wave can exist. One is forward going wave, reverse going wave can exist together. And the third wave is the transmitted wave, what you see here. And there are two possible incidents. One is actually the oblique incident, which is the very general term. And the normal incident is nothing but the wave, the wave traveling direction. If it is z direction, then the normal to the boundary will also be there in the same direction. So that is what we can say as a normal incident. And in the normal incident, you will get the reflected fields also will be there in the same normal, but it will be just opposite of the z vector, or opposite of the normal will be available. And we have defined the incident wave, and the incident wave has its own magnetic field. And by then we have seen the how this reflected and transmitted wave will be available with the very similar boundary conditions what we have seen for electrostatics. In electrostatics, we have seen that the tangential components will be equal in amplitude. So, and in case of the electric and magnetic field, which is traveling in the z-axis, and while the electric and magnetic field, we can say Ex and Hy. So both are tangential components. Therefore, they will be exist in the same magnitude in the other case. But the corresponding impedances, since they are different, then the conversion from electric and magnetic field will be different. You can see that here the magnetic field is calculated with eta1, while in case of the magnetic field in the medium 2 will be calculated in terms of eta2. Therefore, we can say that the electric field will be continuous and the magnetic field will be discontinuous. And using this property, we have calculated the electric field available in both the medium based on the electric and magnetic field. It is calculated. Now, when you add this equation, when you subtract these two equations, you will get ratios of the reflected component with respect to the incident component. And by taking this ratio, you will get a new coefficient called reflection coefficient. The same reflection coefficient we will see till the end of microengineering is one of the most powerful and influential equation in case of electronics and communication engineering. Okay, and there is a two possibility that there is only one possibility that the reflection coefficient will become zero when this eta1 equal to eta2. And so the question is, if there are two structures, let's say this is actually this medium 1 and this is medium 2, and it is having eta2 and it is having eta1. The wave is traveling from one medium to another medium. We don't want any reflections. Only all the power supposed to be transmitted from one medium to another medium. So in order to do that, there's supposed to be existence that eta 1 equal to eta 2, and how that is possible. And even we can see that there are some intermediate material can be placed to match these two mediums. And we will see in near future that how to do such matching of two different medium or the transmission lines all the way. And alternatively, many people used to study the um many people used to study the transmission coefficient with respect to the transmitted wave and the incident wave. And that is just quite opposite to the reflection coefficient. So both are highly relevant to each other. And how to calculate the powers for them, this also we already studied. Now let us take some simple examples to understand this mechanisms. So there are two medium. One is having impedance 100 ohm and another one is having uh, 300 ohm, and there is no phase component. So since the phase component is not available, you can easily assume that the both the mediums are lossless medium, because whenever there is a existence of conductivity, then you will get the phase term will come. So since there is no conductivity, that is why there is no phase term. And we have seen the magnitude of the incident component. So Ex plus 10 means uh, in a, so this is going to be Z axis and the electric field is oscillating in this direction, let's say. So you have E1, sorry, Ex along the X axis. 1 means medium 1, 0 indicate the magnitude, plus indicate the forward wave. And so we have this value. Now we have to calculate the incident wave, reflected wave, and the transmitted waves. So wave means both. We have to calculate both electric and magnetic field. That is what they are simply telling us. Calculate the values of electric and magnetic field in the incident and reflected and transmitted. So first we have to calculate the both the coefficients, that is reflection coefficient and transmitted and transmission coefficient. Reflection coefficient, we know that the basic formula is eta 2 minus eta 1 divided by eta 2 plus eta 1. In some books, you can find the impedance will be used with the term Z. Capital Z will be used like Z1, Z2. So both are ultimately same meaning only. There is no big difference, or there is no difference at all. At least in terms of electromagnetic theory, there is no difference. So we are substituting all the value. We are getting the reflection coefficient is 0.5. So therefore, we can easily calculate the reflected components, magnetic electric field we can calculate. Its magnitude we can calculate. What we have to do, we have to multiply this reflection coefficient and the Ex10 plus. So which will be equal to Ex10 minus. That's all. So we got the value. Then from this, we can calculate the corresponding magnetic coefficients, magnetic fields. So we can calculate, just divide by this eta 1, because both incident and reflected component will be available in the medium 1 only, it will be available. So you have to divide by this eta 1. Here also it is divided by eta 1. Therefore, we calculated the magnetic field. Now, when we calculate the to calculate the power, we have to just multiply the magnitude and divide by 2. Since it is a lossless medium, you will always get the real term alone when you multiply two magnitudes. And the reflected power also calculated. And the third one is the transmitted coefficient. For that, we have to multiply with the transmitted coefficient. So the tau can be calculated with 1 plus gamma. So gamma is already calculated as 0.5. Therefore, this value will be 1.5. So you can easily calculate the other one and the corresponding field. And when you multiply this, you will get the total power. So you could always notice that the total power is 100 watt is incident upon a boundary, and 0.5 is reflected, and remaining power 75 watt per meter square is transmitted inside. since it is a lossless medium. So this is why it is happening. So, but if it is a lossy medium, we can't get this equal values. Means by left hand side equal to right hand side will not count. Let's take another example from study cube. So we have a free space. The free space is defined by z less than or equal to 0. That means the boundary is exactly at 0 and just z equal to negative values, we have free space. Free space means you can easily assume that the mu r equal to epsilon r equal to 1 and sigma equal to 0. So these are the three things you have to remember in case of free space. And the plane wave's magnetic field is defined. The plane wave, you can see that it is existing along the x-axis. So if the wave is traveling and the wave is actually traveling in the z-axis. So the wave is traveling in the z-axis, and we can say that the electric field is available in the x. Sorry, this is magnetic field. Okay. Therefore, in what direction the electric field will be available? So we can easily say that it will be available in the clockwise. When you go, you will see that it is available in this direction, which is negative the minus ay vector. You have to remember that always in the clockwise direction you will find the electric field, and therefore the magnetic field will be available in the anti-clockwise direction. So for this wave, the anti-clockwise direction, we have the magnetic field, and such a wave is called right-handed wave. Similarly, left-handed waves also available, but their properties are a little different. And we can see this 2 omega here, and so omega is nothing but 10 power 8 here. It's nothing but 2 pi f. Now, this is going to normally incident. Therefore, it is a normal incident, and it is going to incident upon a medium which has this epsilon and mu value in the just after z equal to 0 region. So now we have to calculate the reflected and the transmitted wave components of the electric and magnetic field. So for this, we are supposed to calculate the eta 1 and eta 2. Eta 1, we can easily say that it is a free space. It is 120 pi. And eta 2, we can easily calculate by root of mu and epsilon. And this, there is no description. Yeah, there is a description about the medium. It is a lossless medium. So therefore, we can easily use this expression. And we can say that it is nothing but root of mu r epsilon r into 120 pi, because we know that root of mu naught by epsilon naught is going to be 125. So this is what. And this value root of 8 by 2. So root of 8 by 2 is root of 4, which is nothing but 2. So you will get 240 pi, which is defined here as a 2 eta naught, where eta naught is nothing but 120 pi. And we are defining the phase constant. So the phase constant can be calculated by omega c. Here the omega c is calculated for a free space. So that is calculated by 10 power 8 divided by 3 into 10 power 8 meter per second. So which will give only 1 by 3. And when we take the case for the phase constant at the second medium, it is not continuous. It is having some other value. So you have to substitute in this formula omega root of mu epsilon. So when you do this, you will get again 4 is coming, which will give 4 by 3. So this kind of substitution method you have to follow. Okay. So we got the two mediums properties, both eta and beta, both the values calculated. Therefore, we can easily calculate the other components as it is mentioned here. So this is the incident component. So therefore, the incident component will be having same magnitude. Since it is a lossless medium, you'll be having this almost same, but you have to divide with the, you have to multiply with eta. Okay. So in order to calculate the electric field, you have to multiply with the eta with the magnetic field. So you have calculated it. And then when we calculate this, the vectorial component of the electric field, we can easily say that it is a cross product of xy. Okay, you can easily understand this Whenever you multiply z into y, you will get minus ax, because you have reversed the uh, mm, you have reversed mm, the 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 order. Okay, so it is z into x like that. Similarly, when you skip, let's say and y and x, when you multiply, you will get minus a z will come. So whenever you change the order, you can easily understand that it is going to be negative of the remaining vector. So that is why you are getting minus a. So this can be understood in the other way also, clockwise, anti-clockwise like that. So when you substitute, you will get the magnetic electric field is coming. Magnetic field is already available. Sorry. Now we have to calculate the reflection coefficient. The reflection coefficient calculated with the same quantity. Since eta naught is already available, we can cancel out that term. We got this 1 by 3. Therefore, the reflected component is available. We can calculate the reflected component just by this gamma alone. We have to multiply. And similarly, magnetic field. We already have the magnetic field term. Just multiply with the 1 by 3. That's all. You will get it. Then same thing we have to do for the transmitted coefficients. We can easily calculate the values. I believe it is very easily understand by seeing the problem. It's a very direct one and easily understandable one, and that is the advantage of statistical book. Oh, if you consider the oblique incident means it is the incident will be having its own angle with respect to uh, the the normal to the boundary. So we know we can see that this is the boundary, and we can see this is the normal to the boundary, and the wave is traveling in the let's say in the z direction. Therefore, this we will say this is a normal to the boundary, and this is the opposite to the normal to the boundary. So this is what we say the uh, the line which is actually drawn normal to the boundary. And with respect to the normal, we will be seeing that the incident wave is actually uh, having angle of theta I. So this theta I will be equal to 0 for normal incident. That is what we have seen here as a normal incident. Here the theta I is not equal to 0, and all other cases are nothing but oblique incidents. And in this case, how this electric and magnetic field will behave? Can we say that the both electric and magnetic field will be still transverse to the boundary? Or no, the condition is not possible, because this is having its own angle with respect to the surface itself, surface direction. So obviously, this angle will create the normal component as well. So, and the vertical component which is having, that is also will be having its own normal component. So it is, we can't say that both the components are simply transverse to the boundary itself. So we can't directly calculate this value. We're supposed to calculate both the values. So for this, alternatively, people have come up with this angle theta I itself. Okay, so we can easily utilize to calculate all the quantities. So a incident wave is traveling, and in order to say the wave is actually this is from the top view. Okay, you can assume that this is the z direction. The electric field is traveling in this way, and the magnetic field is traveling in this way. And we are seeing from this top view. Whenever we see from the top, we can say that the electric field is pointing us. Whenever it is pointing us, you have to say this, and you can see that the wave is transverse wave, and that is defined by this dotted lines. Okay. Otherwise, you can see that there is another component which is along the which is normal to the traveling wave direction. So both are having its own angle theta I. And whenever it is incident, there will be a reflected component. The reflected component is also having its own angle with respect to normal line. And it is going to transmitted inside. And often it is referred as refracted wave. And the refracted wave will be having its own angle, since there is mediums are having different, we will be having discontinuity in the electric and magnetic field. This obviously will change the theta t, that is the transmitted wave angle. So which is called the angle of refraction. So this angle of refraction is never be equal to theta I. So now we have to calculate the magnitudes of this each component and the relationship between them. So it is very common. We already studied about the Snell's law, which is often applicable to or used in the optical theories, but it is very well can be done with the electromagnetic waves. So we can easily say that theta I equal to theta R. So the angle of incident will be equal to angle of reflection. And how to calculate for refraction? For this, we have to use uh, the law of refraction. The law of refraction says that the sine theta I by sine theta t will be equal to the ratio of the corresponding wave numbers. Wave numbers are nothing but the corresponding phase coefficients. So this phase coefficients can be easily modified to the refractive index. This is what you have studied as a law of refraction. And here we can see the refraction and how this beta is connected. Now, from this, we can easily calculate theta. So if we know theta I, we can calculate, and we know the epsilon r1, epsilon r2, sorry, yeah, mu r1, mu r2, sigma, all the value once it is done. So you can easily calculate this n1 and n2. Therefore, we can calculate all the values. Theta I, theta r, theta t, three values can be calculated. Once this value are calculated, then you can easily calculate the reflection coefficient using these simple formulas. And since it is open book test, you can easily remember this. And all these two components are divided as the parallel component and the normal component. So you can see which is this is the parallel component. So here the magnetic field is the parallel component and the electric field is the normal component. Both are almost same expressions. Only the difference will come as here it is first starts with Z1 and here it is Z2. Here it starts with Z2 and Z1. So that is a minor difference. Otherwise, almost everything is same. And the denominator also will be same only. So this is what we have seen for the reflection coefficient and the transmission coefficient. Since there are four values, they always referred with the matrix. So here you can see the reflection coefficient is a diagonal matrix, and there are two vectors. Vectors will be nothing but column matrix. It is available. So you can calculate simply same as that of this. When you multiply the incident component with the reflection coefficient, you will get the reflected the magnitude of the reflected wave can be calculated. Same thing applicable to transmission coefficient as well. So the only difference is this angle which are created with respect to the normal to the surface. There is a simple example. The incident electric field is actually given and it is linearly polarized. Linearly polarized means only this vertical component or horizontal component alone supposed to be available. And in this case, we can assume that it is available with the normal component alone. And it is incident onto the boundary of a lossless non-magnetic medium. Non-magnetic medium means it is not having magnetic property. Therefore, mu r will be equal to 1. Only it is having dielectric property. With the angle of incident is given. And we have to calculate the electric field. Okay, the electric field is parallel to the, so only we have the parallel component. Therefore, we have the electric field as a parallel component. We can call it as E parallel. Sorry, E parallel. We are going to assume. Now we have to calculate the refraction angles, the electric field in the both in the medium 1 and 2 we have to calculate. So medium 2 means it is transmitted, and the reflected one which is available in the medium 1. So whenever we have such components, we're supposed to be very careful about dividing the electric field to get the magnetic field. And so it is a linearly polarized and non-magnetic medium. And so only we have parallel component alone available. Therefore, the vertical component is need not to be calculated. We need not to calculate this. These components need not to calculate. Only parallel component is going to exist. So first we are calculating using Snell's law. We have calculated the reflection and refraction angles. I think this is very pretty simple. Simple mathematics is used. And after finishing this calculation, we are going to calculate the impedance of both the medium. And since the incident is happening in the free space, its impedance is 377 ohm, or you can say it is a 120 pi. And here the medium 2, which is a non-magnetic medium, which has this impedance. And now you can easily calculate you can easily substitute in this formula. In this two formula, you have to calculate R parallel and T parallel you have to calculate. So you can see that the T parallel is calculated, and therefore the electric field T transmitted wave, the parallel component is calculated. When we calculate the magnetic field, we have to divide by the corresponding impedance. And same thing we can do for the reflected. While you do the reflected one, you can clearly notice this difference of negative sign. So this indicate the wave is traveling in the backward direction. So that's all it is. I think very pretty simple for workouts. So where this calculations are used, how practically we can use it in multiple ways. Here you can see that the assume that the earth is here, and just above the earth we have free space. So here we have eta 1 and eta 2, and we have a base station. The base station is going to transmit two waves. One is the wave is actually traveling in the perpendicular direction. You can call it as E perpendicular, and corresponding the tangential component is available, that is E parallel. And both the field components are, and since both the fields are available, you can call this as circularly polarized. And this wave, when it is directly traveling from transmitter to receiver, you can call it as a direct wave, or it is nothing but line of sight. But the reflected component due to the earth could be possible, and the wave is traveling towards the earth and hits and it goes back. And whenever it goes back, there is this reflected wave, and you will have the refracted wave. So this is going to be the T. This is going to be because of the reflection coefficient gamma. And since both the components are available, the very important question will come: how about the reflected one? In the electronics and communication engineering, if you notice that uh, when we transmit the power about 100%, and the energy, now you can see that only two possible ways. One is here the 50% is traveling, here the 50% energy is traveling. Of course, this 50% is reached here, but in the reflected component, we could not say that how much power will come. Totally, let's say it is going to be about 75% power is received, and 75% out of 100%. So there is a big question that if we send 1 watt power, we may get, let's say, 0.75 watt power uh, into out of this 1 watt. Okay. So in this case, if the receiver demand with respect to the noise level available, if we need more power, then we can't simply rely upon only the direct wave. So we also need the reflected component. So that is why still ground wave reflection is used for the communication purpose, particularly for the mobile phone application. People still use both the line of sight and non-line of sight waves for the power reception, so that we will get sufficient power to demodulate the signal. So now most of the cases you will get the dry ground as the earth in the city or in the village or in the rural area also. So you'll be having mostly dry grounds will come. But in some cases it may be full of trees. It may be some if it is a rainy season, the earth may be wet. So its conductivity as well as the dielectric constants may vary. So this is actually calculated using a study which we call Brewster angle microscopy. So using this, when they calculated it, they found for dry ground, which is the most common one, we can see that the reflection coefficient for perpendicular and the parallel components, similarly for transmitted transmission coefficients also it is calculated. This is the angle of incident. So with respect to that, this is the normal to the surface, this is the surface. The angle of incident is like this. So this is what theta is. When the theta I equal to zero, theta I equal to zero means normal incident. Okay, so both the components are equal. Okay, both normal and the reflected component both are actually equal, and it is same for transmitted coefficient also. But when the angle is keep on increasing, okay, and it is keep on increasing, let's say it is very close to 50 degree. With respect to 50 degree, we can it is approximately here, let's say. So then you can see that the the perpendicular component is reflected more than that of the parallel components, which means that the parallel components are going inside the earth and only the perpendicular components are reflected more. And you can see that the reflection is keep on increases as this angle of incident is increasing. So if this is the tower and you are still decreasing you are increasing the angle of incident, the reflection will takes place more for the perpendicular component rather than the for the parallel component. Parallel component is keep on decreasing. At a particular point, it is reaching almost zero, which means that at a particular angle, let's say the 70 degree, there is no reflection of this parallel component at all. So this is what often referred as Brewster's angle, and this experiment first done by I think James Brewster. So based on his experiment, this been found, and interestingly, after this angle, you will see that the reflection will happen very quickly, and after this 70 degree, I'm not sure that any tower will be having that much height. So this is about 10 feet, 20 feet height. People won't provide such a tower height. It will be just above 40, 50 feet. So the for a wireless communication, the tower will be available with the angle of incident with greater than 70. So obviously, the important thing is we can't retrieve this parallel component. So 100 percentage energy. Okay, out of that 50 percentage is traveling. In that 50 percentage, 25 percentage is perpendicular component and 25 percentage parallel component. In that sense, we will simply lose the 25 percentage and we can get only the 75 percentage of the reflected. And since we can't say that both air medium as well as the ground has uh, lossless, but sometimes it will be lossy medium. So if they are lossy medium, then further losses might be available. So this experiment simply tells that for a good communication purpose, better use only linearly polarized, that to vertically polarized component alone if you use, that is for good. And similar experiment can be done for other cases also. And not only this, now I think many of you are using polarized sunglasses. Whenever you use the polarized sunglasses, the medium will be allowing only perpendicular component or parallel component. Any particular component will be available. And in case of in case of sun, it will be having both component. When they reflect and it will come to you, both the components will be available, but one will be having phase difference with another. So this may create some confusions to your eye. So this is what happening when there is a strong reflection due to this ground or due to the mirror, whatever it is. So to avoid that, if you use polarized glass, you will receive either vertically polarized or horizontally polarized. Any one only will be available. So for instance, this is when you polarize with vertical, and this is when you rotate for 90 degree, when you polarize with horizontal. So you can see that the reflections are completely removed. So we can easily say that the reflections, most of the reflections by this ground is largely due to the vertically polarized component. Therefore, you can clearly see the view of this in this scenery. So this is how actually we can utilize this this oblique incident and the concept of polarizations in a broader way. And for this, we need some type of microscope component, and this will be nothing but multi-wavelength laser. And here we will keep the sample. So the reflection will be calculated and the amplitude will be calculated. So we can produce both parallel perpendicular component, parallel component, and here also we can calculate both. And for this, we need some kind of fibers to get the polarization properly. Uh, so by this, nowadays the studies are going in various aspects like anti-glare uh, specs, and similarly for the windshield of the car also we can have such a, and what type of material we supposed to coat. Many studies are going on. For this, we're supposed to be very clear that this particular theory and the how this impedance with respect to different material properties. So the material property is very important in that way. So by this, actually, we have completed this module 3, module 5 also. So, and in future, we will see next to 3 classes, I am going to dedicate this 3 uh, numerical problems on this 3. So many numerical problems, and the earlier question papers also we are going to see. So if you have any questions, you can